Have you ever really stopped to think about time? We live our lives moving in just one direction, from yesterday to tomorrow. An egg cracks, but it never, ever uncracks. A glass shatters, but it doesn't just put itself back together. It seems so obvious, right? But why? What's the actual physical law that stops time from just running backwards? Well, today we are digging into one of the biggest, deepest mysteries in all of physics, the arrow of time. All right, so here's our game plan. I want you to think of this as a kind of cosmic detective story. First, we're going to lay out the central paradox, the main mystery. Then we'll follow three major clues, one from thermodynamics, another from the very beginning of the universe, and a final, really strange one from the world of quantum mechanics. And all of that will lead us to the final, timeless mystery. So let's start our investigation with the paradox itself. It's something we see every single day, something so common we barely even notice it. But lurking underneath is a really profound puzzle in physics. I mean, just picture it. You drop an egg, and it splatters on the floor. Or maybe you bounce a ball, and it loses a little bit of energy with each bounce until it just stops. These things seem completely normal, totally unremarkable. It's just how the world works. But now, imagine you hit rewind on a video of those things. The shattered mess of an egg miraculously reassembles itself and flies right back up into your hand. The ball on the floor suddenly starts gathering heat from the ground and bouncing higher and higher. It feels absurd, impossible. It feels like you're watching magic. So what's the physical reason we can't do that? And here's where it gets really weird. Most of the fundamental laws of physics couldn't care less about which way time is flowing. Gravity, for example, is time reversible. If you watch a video of a planet orbiting a star, it looks just as plausible forwards as it does backwards. The equations work perfectly in either direction. And yet, the world we actually live in, the big macroscopic world, clearly has a one-way street. This is the heart of the mystery we're trying to solve. Okay, so let's move on to our first major clue. Back in 1927, the British astrophysicist Arthur Eddington actually gave this whole thing a name. He called it time's arrow, and he had a really powerful idea about what was pushing it forward. Eddington had this brilliant insight. He realized that the direction of time is somehow fundamentally tied to the increase of randomness or, well, disorder. He argued that this one-way property of time, this arrow, is the only thing in all of physics that truly tells the future apart from the past. Now, this concept of disorder has a proper scientific name. It's called entropy. And the rule it follows is called the second law of thermodynamics. It's one of the most solid fundamental laws in the entire universe. And it basically says that the total entropy of a closed system, like say our universe, can only increase over time. It never, ever goes down. Just think about it in a way that makes sense. There's only one way for a deck of cards to be perfectly ordered, right? Ace to king, all suits together. But there are a bazillion ways for it to be shuffled and messy. Your bedroom can become messy in a million different ways, but there are only a few ways for it to be truly neat. Systems just naturally drift from states that are unlikely, low entropy, high order, to states that are overwhelmingly more likely, which means high entropy and high disorder. The egg shatters because the shattered state is just so much more probable, so much more disordered than the perfectly intact state. This is the thermodynamic arrow of time. But you see, this clue actually makes the mystery even deeper, because if the universe is always getting more disordered, well, that raises a really big follow-up question. And this one takes us from a messy room all the way to the entire cosmos. So let's just follow the logic here. We've established the second law is pretty solid. Entropy, or disorder, always goes up. Okay, so if the universe is constantly getting messier and more chaotic, that logically means that in the past, it must have been less messy. And if you go all the way back, it must have started in a state of incredible order, of extremely low entropy. So that leads to this huge question. Why? Why was the beginning of everything so special and so tidy? To find the source of all that primordial order, we have to wind the clock all the way back. I mean, all the way back to the very, very beginning of time itself. It turns out the Big Bang wasn't just the start of all the matter and space we see, it was the start of time, too. The universe began in this incredibly dense, smooth, and highly ordered state. So the cosmological arrow of time, the reason today is different from yesterday, is a direct result of those unique starting conditions. Our universe's entire journey and time's one-way direction is really just the process of it unwinding from that super-ordered beginning toward a future that's guaranteed to be messy and high entropy. So far, this story kinda hangs together, right? But now we have to get to our final clue. And this one is a truly mind-bending twist from the absolute frontiers of physics. It asks a question so profound it challenges everything we've just talked about. What if time isn't actually a river that flows from past to future? What if it's something else entirely? What if our feeling of time passing is, well, an illusion? Now, this isn't just philosophers asking weird questions. It's a real possibility that comes out of our deepest theories about how reality works. And this idea gets very real when you look at the actual math. When physicists tried to combine quantum mechanics with general relativity to write down one single equation for the entire universe, something really shocking happened. The variable for time, the letter t, just disappeared. It vanished from the equation. This thing, the Wheeler-DeWitt equation, suggests that if you could somehow step outside and look at the whole universe at once, it would be timeless, static. So, how do we get time back? If it's not in the master equation, where does it come from? Well, one of the most fascinating theories out there says it emerges from quantum entanglement. You know, that weird link where two particles can be connected, mirroring each other no matter how far apart they are? The idea goes something like this. You can split the timeless universe into two entangled parts. Let's call one part a clock, and the other part is everything else. For us, living inside the everything else part, when we look at the clock, our observation locks in its state. And because the two parts are entangled, that act simultaneously locks in our state at a corresponding moment. So in this view, time doesn't flow. It's an emergent property that comes from the quantum connections between all the pieces of the universe. Okay, wow. So where does all of this leave our investigation? We've gone from a simple cracked egg on the kitchen floor to the Big Bang, all the way to the quantum fabric of reality itself. Let's try to pull our key findings together. We've basically uncovered three different but connected arrows of time. First, there's the thermodynamic arrow, the one we see in our everyday lives, which always points in the direction of more messiness, more entropy. Then there's the cosmological arrow, which explains the first one. It's basically a relic of the universe's incredibly ordered beginning at the Big Bang. And finally, the quantum arrow, which suggests something truly wild, that time itself might not be fundamental, but is just an illusion that emerges from the strange rules of quantum entanglement. In the end, the case is still wide open. So what is time? Is it a fundamental river that flows ever onward from that low-entropy spring of the Big Bang? Or is our entire experience of its passage just a kind of shadow play, an illusion created by the bizarre, timeless connections that bind our universe together? This is still one of the biggest unanswered questions in all of science, and honestly, that's what makes it so amazing to think about.